All right. All right, boys and girls. I want to go through an example of writing out the electron configuration for an element. I assigned to you the electron configuration for aluminum as part of yesterday's or this morning's homework. So I'm not going to do aluminum, which is atomic number 13. That'd be 13 electrons. Let me choose, I don't know, let's say nitrogen. All right. Now, nitrogen has 7 electrons. And where do we place them? Well, on page 148 of the readings that I supplied to you this morning, at the very top of the page is something called an off-bow diagram. And that's really where I would suggest you start. All right, if you look up along the vertical axis here, you'll notice that it's labeled as energy with the arrow pointing up, so that means increasing energy. The lowest energy orbital is the 1s, and according to Hund's rule, we always put electrons in the lowest energy orbitals before we begin filling the higher energy orbitals. Now, in this diagram, in this off-bow diagram, you notice next to the 1s is a single square. That means that it is a single orbital. And within that orbital, we could put 2 electrons. We signify those with up and down arrows. The up means plus a half, the down means minus a half. Those are the electron spins. Right? After the 1s comes the 2s, and the 2s is able to hold 2 electrons also. But notice the next set of orbitals, the 2p's, come in groups of 3s. And that has to do with the fact that when we have p orbitals, we're dealing with L equal 1. And when L equals 1, M could be -1, 0, or +1. That's 3 different values. And that's why when we're talking p orbitals come 3 to a group because of this. And you'll notice up here the d's come 5 to a group. Now there's no f orbitals listed on this particular off-bow diagram, but if there were, we would see those f orbitals with 7 boxes after them. All right. Anyhow, let's go ahead and start this. If I could find my eraser. All right. So we're going to start in the 1s, and we'll put 1 up arrow, 1 down arrow. Then the next orbital, energy-wise, is the 2s. That would be 1 up, 1 down. Now what we do is we count the arrows. There's 1, 2, 3, 4. Those 4 arrows mean that we've found a home for 4 of the 7 electrons. All right. We have to find a home for the other 3 to get a total of 7. Well, what's the next orbital energy-wise? The next one just above the 2s is the 2p. Now they have it shifted over a little bit on the diagram. You'll see that shifted that way, but that doesn't really mean much anything. They do it just to make a nice looking chart there. All right. So I have to put 3 electrons in here. Now, according to Hund's rule, I believe it is, the F-bar rule tells us we have to put them in order of increasing energy. Hund's rule tells us that when we're placing electrons within similar energy orbits, like these set of 3 orbitals in the 2p level, that we do not pair the electrons unless we must, which means that we're going to put an up spinning electron in the first p orbital, an up spinning electron in the second p orbital, and an up spinning electron in the third p orbital. All right, we wouldn't put them in as an up down and then an up. All right, and then we would have one of the p orbitals with nothing in it. That would be wrong. That would be a violation of Hund's rule. All right. So this is one way of writing the electron configuration of an element. All right. Now we will often take this method or this information and write it down in a more condensed version. We write it like this: 1s2, right? The 1s is the same as the 1s here, and the 2 means there's 2 electrons in there. Then above that, 2s, and there's 2 arrows, so it'd be 2s2, then 2p. Now we have 1, 2, that's 3 electrons. Now, if we write the electron configuration like this, we lose a bit of information. It's not shown in this type of configuration that these 3 electrons are unpaired. Up in this type of notation, we do see that those electrons are unpaired. All right, let's try another one. All right. Let's, before we do anything, let's put this off-bow diagram back in here. 1s, and then there's a single orbital for 1s. 2s, there's another single orbital. 2p would be in this group of 3 orbitals. And above that is 3s, and then 3p. These p's come in groups of 3 also. And then above that is a 4s. All right. Again, all I am doing is taking this information right off of the page from the PDF file I gave you. Again, it's page 148. All right, now I'm stopping at 4s, but if we were to go beyond that, it would be 3D, and then 4P, then 5S, then 4D. And again, this is an abbreviated version of all of the orbitals. All right, this stops at 4D. The orbitals keep going. Anyhow, let's choose another element here and see how we could plug in for this. Let's choose potassium. Potassium, whose symbol is K. All right, and right here on the periodic table, K is atomic number 19, so that's 19 protons. Now, if it's a neutral atom, that would also lead us to believe that that would be 19 electrons, equal numbers of positive and negatives. All right, so these 19 electrons are going to are going to be showing up in our electron configuration up here as 19 arrows. Some up, some down. All right, so let's just go ahead and do that. All right, where do we begin putting these 19 electrons? Well, we start at the lowest energy orbital. 1 up, 1 down. All right. Then we go up to the next one. 1 up, 1 down. That's a total of 4 electrons. We got more to go. That's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and the 4s with just a single electron in it will be the 19th electron. All right, so this is the proper way of filling up the orbitals with 19 electrons, or 19 arrows, and we know that that represents the electron configuration for the element potassium. Now, if I wanted to write this in a more condensed way, I would write this out starting with the 1s, 1s2, and then 2s2, that takes that off, and then 2p, 2p, and that's got 6 electrons, so that's gone. 3s2, that's gone. 3p6, that's gone, and then 4s, but that's a 1, 4s1. So there we go, that's potassium right there. Right, the electron configuration notation for potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If you wanted to do the actual energy level diagram, you would have these boxes and have it just the way we have it here. Okie doke, folks. Hope that helps.